That is, we typically don't let them close all the way. We force them to keep a minimum airflow, even at times when we would like less airflow. There are pros and cons to doing this. First off, it prevents us from operating at low flows, which again can drive up the energy consumption and be bad for the equipment. Secondly, it prevents operating the fan in the surge region, which can be damaging to the fan. Lastly, it allows us to ensure adequate amount of ventilation air is being provided to the space. We will talk more about how that is exactly done in the next lesson on ventilation, but for now just know that we obviously can't be bringing in ventilation air if we were cutting off all of the airflow into a space. A limitation of setting minimum flows in our VAV boxes is that it can create an issue of overcooling the space. If the controller is telling the damper to close since the space temperature is dropping, but the damper is at a minimum position, more cold air will be sent to the space than required. Thus, the room air temperature will drop somewhere below set point. The comfort issue that ensues can be addressed in one of two ways. Either we install a reheat capability in our VAV boxes, or we implement a supplier temperature reset schedule. Let's talk about the VAV with reheat configuration before we get into reset schedules. The VAV with reheat configuration is shown here. These seem to be very common in the Air Force. This system should look very similar to what we just saw, only now we have brought back the boiler and hot water loop and installed reheat coils in our VAV boxes. So our VAV boxes now have two items in them. The damper, which has the ability to modulate, and a reheat coil, which has a control valve which can modulate the flow going through it. So let's see how this all works. Back at the air handling unit, we can modulate the cooling coil's control valve to track on a discharge air temperature of about 55 degrees Fahrenheit. So no change there. We have seen this before. Now we have cool air in the supply duct available to provide cooling to the various zones. At each zone, you again have a temperature sensor which measures the space temperature and sends that information to a controller located in the VAV box. Only now, the VAV box has two control devices in it, the damper and the hot water control valve. How exactly the controller controls these two devices is often a point of confusion, so let's try to clarify that here. One quick note, I'm going to present a control sequence here that is by far the most prevalent one used in controlling VAV boxes. There are some other approaches, however, but we can save that for a discussion on the LMS. Say a particular zone was requiring a lot of cooling. Thus, the controller has commanded the control damper fully open to ensure the maximum amount of airflow is provided to the space. At this point, since we are in cooling, it would make no sense to be sending flow through the reheat coil. But then the cooling load in the space starts to decrease. Maybe people leave or the sun goes down, who knows, but the cooling requirements are now less. Initially, since the damper was fully open, we will start to overcool the space a bit. The controller would recognize this drop in space temperature below set point and command the VAV box damper to start closing. If the cooling requirements continue to drop, eventually the VAV box damper will reach its minimum position. Again, we dictate a minimum position to both ensure minimum ventilation requirements are being met, as well as to allow for a path for a minimum amount of air to flow so we don't deadhead the fan. Alright, so the cooling load continues to drop and we reach minimum setting on the VAV box damper. Say the cooling set point was 74 degrees Fahrenheit. If that minimum flow is still providing more cooling than need be, the space temperature will fall below cooling set point. The controller will initially do nothing. It will allow the space temperature to continue to drop. Maybe the room temperature will settle at 72 degrees Fahrenheit, at which case the controller will just keep minimum flow going through the VAV box. But if the space temperature continues to drop, it will eventually reach a predefined heating set point, which we will say is 71 degrees Fahrenheit in this case. If the temperature drops below this heating set point of 71 degrees Fahrenheit, that would indicate to the VAV box that we are now in a heating scenario. Thus, the controller will lock the damper at minimum position, and now start to modulate the reheat valve open. From that point forward, the reheat valve will modulate to maintain the heating set point in the space. If a bunch of people return to the room, the temperature may again start to rise above 71 degrees Fahrenheit. The reheat valve will modulate towards a closed position in order to maintain that 71 degrees set point. If the valve completely closes and the temperature continues to rise, and it eventually rises to a temperature above the cooling set point, the controller will again start to modulate the VAV damper to maintain the cooling set point. So you can see the controller modulates both control devices, the damper and the valve, but never at the same time. When in cooling mode, the damper modulates and we maintain a constant supplier temperature of 55 degrees Fahrenheit. When in heating mode, the airflow rate provided to the space stays constant, and we modulate the supplier temperature by use of the reheat coil. Remember how we said maintaining a minimum setting on the VAV box airflow can create an issue of overcooling for the space if the cooling requirements were quite low? Well, providing this reheat capability helps curb some of those comfort complaints that would occur from overcooling the space. So the explanation we just provided is how a VAV with reheat system configuration should be controlled. However, there are some inherent issues here. For one, if we are cognizant enough about energy conservation to install VFDs on our fans, we are probably not too happy with the energy waste that comes from operating the system in heating mode. What energy waste, you might ask? Well, think about what is happening in heating mode. The air is cooled to 55 degrees Fahrenheit coming out of the air handling unit. Then it is heated up by the VAV box to somewhere on the order of 75 to 90 degrees Fahrenheit, depending on the heating requirements of the space. So we pay to cool it down, and then we pay to heat it up. That is wasteful. Now, we can't always get away from this. During the spring and fall, there are days when one zone in the building may be requiring heating, while another zone may be requiring cooling. Thus, operating the system in this manner we just described allows us to provide heating to one zone and cooling to another. The ability to address this diversity of thermal loads in a building is a great attribute of VAV with reheat. But if it gets to the point where all the zones are requiring heating, what is the point of controlling the discharge air coming out of the air handling unit to 55 degrees Fahrenheit if all of that air is just going to be reheated at the various VAV boxes further downstream? For such situations, there are two approaches we can take to cut down on such energy waste. The first approach is actually quite simple, and actually it's done at a lot of the bases in the Air Force. We just remove the capability to provide cooling during the winter and remove the capability to provide heating during the summer. That is, we drain the chilled water lines for the winter and disable the boilers in the summer. That way, we won't be paying to cool the air to 55 degrees Fahrenheit coming out of the air handling unit, only to heat it up again at every VAV box downstream. This process of draining chilled water lines might also be required to prevent freezing of the pipes that don't contain any glycol. But some of you might be thinking, if every space is really in heating mode, wouldn't the outdoor air temperature be cool enough to just open the outdoor air damper more and bring in enough cool outside air to bring the temperature to 55 coming out of the air handling unit? That way we don't have to pay to run the chiller and chilled water pumps. And that is a great point. Such a control strategy is called an air-side economizer cycle. That cycle will be discussed in more detail 2 lessons from now. But for now, know that the economizer cycle is great to implement when large portions of the building are in cooling mode. However, if the whole building is requiring heating, utilizing an economizer cycle to drop the temperature coming out of the air handling unit will only increase the heating requirements of the reheat coils at the VAV boxes. So the economizer cycle has a lot of nuances that need to be programmed in to ensure that it only operates when it will truly be saving us energy. One way to help out with this is to implement a supplier temperature reset schedule. This second approach can be done independently or in addition to draining chilled water piping. So let's review what we mean by a reset schedule again. A reset schedule is basically a schedule which changes the set point in a closed control loop based off of some other variable. You will often hear the term supplier temperature reset schedule when talking about all sorts of different air system configurations, to include the VAV with reheat configuration we have been discussing. But let's be clear. The supply air temperature they are referring to here is the temperature of the air coming out of the air handling unit, not necessarily the temperature of the air being supplied to each zone, as that will vary depending if the reheat coil is engaged or not. So how exactly would we implement such a reset schedule? First off, let's define again what the issue is. Again, if all of the building is in heating mode, it doesn't make much sense to cool the air to 55 degrees Fahrenheit at the air handling unit just to heat it back up at the VAV boxes. So we could change the temperature set point for the air coming out of the air handling unit during such periods to minimize that waste. We could do that in one of two ways. First, we could change the set point based off of the outdoor air temperature. Here, we are basically assuming that when it is below a certain temperature outside, a large portion of the building is probably going to be in heating mode. Thus, we adjust the set point of the air leaving the air handling unit to minimize the waste of reheating such air. The temperature set point could follow a pattern like the one shown here. When the outdoor air temperature is above 65 degrees Fahrenheit, we assume it is beneficial to just cool the air down to 55 degrees Fahrenheit. When the outdoor air temperature is below 55 degrees Fahrenheit, we assume the cooling requirements of most spaces are greatly reduced, and some spaces may potentially be in heating mode. Thus, we raise the set point temperature of the air coming out of the air handling unit to 60 degrees Fahrenheit. 60 Fahrenheit is conservative. It allows us to still provide cooling to the spaces that need it and minimizes the amount of energy waste that occurs at the spaces that require heating, since now the reheat coils for those VAV boxes don't have to raise the temperature of the airstream quite as much. This approach doesn't completely cut out all the reheating that can occur, but it reduces some of the energy waste, all while maintaining the ability to provide both heating to some spaces while supplying cooling to other spaces. We are essentially sacrificing a little energy to ensure occupant comfort in all spaces. So this is how the supply air temperature can be reset based off of outdoor air temperature. This is becoming an old way of thinking, as many spaces in commercial buildings are dominated by internal heat gains from occupants, lighting, and equipment. That means that maybe a particular space would require heating on a Monday when it's 45 degrees outside. However, on Tuesday, with outdoor air temperature also at 45 degrees, the space might actually be requiring cooling due to an increase in occupants and an increased use of lighting and equipment. So the new way of thinking is to reset supply air temperature based off of some other variable. That other variable would be that of the return air temperature. In this approach, we have a temperature sensor located in the common return duct. Say the cooling set point for all the zones is 74 degrees Fahrenheit. If the common return air temperature is measured to be 72 degrees Fahrenheit, that would indicate that at least one of the spaces is being overcooled. That is, the VAV controller is saying, "We're getting cold, we want less airflow," but the VAV box damper is saying, "Suck it up, I can't close anymore." Or it may have even gotten to the point where the reheat valve has started to open. Thus, when anything less than the cooling set point of 74 is sensed in the return duct, this would be a good time to start increasing the supply air temperature. So a supply air temperature reset schedule following this approach may look something like this. If the return air temperature gets to the point where it is reading 71 degrees Fahrenheit, which again was our heating set point, that would be an indication that most of the building is in heating mode. Now, you might be wondering why we're not more aggressive with this supply air temperature reset schedule. If a return air temperature of 71 is an indication the majority of the building is in heating mode, why not bring the supply air temperature up to 65 or maybe even 70 degrees Fahrenheit? That would prevent reheating of the air further down the duct path in the VAV boxes. Well, for one, oftentimes the air coming out of the air handling unit is going to be around that temperature anyways. That is, we didn't operate a chiller and chilled water pumps to bring the temperature down to 60 degrees Fahrenheit, and we didn't implement an economizer cycle to bring it down either. We simply ended up at this temperature for reasons out of our control, like adhering to code requirements to bring in the appropriate amount of ventilation air. Imagine the return air temperature is at around 71 degrees Fahrenheit, and the outdoor air temperature is at 49 degrees Fahrenheit. And for this example, to meet the ventilation requirements, let's assume we need to bring in 50% outdoor air. The mixed air temperature entering the air handling unit would end up being around 60 degrees Fahrenheit. So again, it's not like we purposely wanted to bring that temperature down. We just had to in order to meet ventilation requirements. The second reason we don't want to bring supply temperature set point much above 60 is for wasted fan energy. If we did have spaces in cooling, an increase in supply air temperature may result in the dampers opening more, which would require the fan to speed up more and consume more energy. And the final reason we don't want to get too aggressive with the supply air temperature reset schedule requires that we do a little case study. Here at AFIT, when classes are in session, we can have some pretty jam-packed rooms. Many of our classrooms have an exterior wall, and since we are in Ohio, there are times when the cooling requirements for the space are quite high and times when they are quite low, even when fully packed with students. In a classroom setting, however, 35 students breathing is going to produce about the same amount of moisture gain in a space regardless of how large or small the sensible cooling requirements for the space are. Since the room's VAV box is only controlling for temperature though, there may be some ramifications when it comes to humidity levels in the space if we get too aggressive with the supply air temperature reset schedule. For example, students put off about 110 BTUs per hour of latent heat energy just by breathing. 35 students would equate to a latent load of about 3,850 BTUs per hour. Say it's a pretty hot day out there and the total sensible load is around 26,000 BTUs per hour. If the rest of the building was in cooling mode as well, the supply air temperature set point would probably be around 55 degrees Fahrenheit. So let's run some numbers. Assuming a room air temperature set point of 74 degrees Fahrenheit, we can calculate the airflow that would need to be coming into the space to meet the sensible load. So this system would be putting in 1244 CFM into the space. What relative humidity would the space balance out at? Let's go to the latent load equation for the space. We can find the humidity ratio of the supply air by assuming the supply air is coming in at 55 degrees fully saturated. Thus, from the psych chart, we get it to be around 0.0094. So that humidity ratio would balance out at about 0.0100 pounds mass water per pounds mass air. But that value probably doesn't mean much to you. So let's go back to the psych chart to see what relative humidity that would be at a room air temperature of 74 degrees Fahrenheit. We are looking at about 56% relative humidity. That seems pretty bearable. Now let's imagine that the majority of the building is empty, and this lack of internal heat gains has resulted in a drop in return air temperature. The reset schedule will then impose a higher supply air temperature set point. But our space is still occupied. The latent load is the same, at 3,850 BTUs per hour, and the sensible load is slightly reduced, but it's still about 20,000 BTUs per hour. If the reset schedule was quite aggressive and forced a 65 degree supply air temperature, what effect would that have on our room's humidity level? Well, let's see. Going through the same set of equations as before, we find the required flow rate has now increased to 2,020 CFM. We will come back to that value here in a minute. First, let's try to figure out the room's humidity level. We will first need to find the humidity ratio of the supply air. But now, on a very humid day, which occurs often here in Dayton, Ohio, there is a possibility of the humidity of the supply air to still be fully saturated, but this time at 65 degrees Fahrenheit. From the psych chart, we find the corresponding humidity ratio to then be 0.0133 pounds mass water per pounds mass air. Solving the latent equation for the space, we find the humidity ratio for the room would settle around 0.0137 pounds mass water per pounds mass air. Putting that in layman's terms, that corresponds to a relative humidity of 75% at 74 degrees Fahrenheit. Such a humidity level can be distracting to anyone, especially to students trying to learn. So what is the moral of the story here? In humid climates, don't get too aggressive with your supplier temperature reset schedules. It is never advised to bring the set point any higher than 60 degrees Fahrenheit in humid climates. Otherwise, there will be times when the relative humidity of the space will creep into unacceptable levels. It is recommended that the supplier temperature be capped at 65 degrees Fahrenheit in drier climates, as space humidity is not as big of a concern. Additionally, in the example we just saw, the CFM of the air increased from 1244 to 2020 CFM. That 62% increase in airflow would result in an increase in fan power requirements associated with this space. So this has been a very lengthy discussion on supply temperature reset schedules. I have been stuck in buildings where too aggressive of set points were imposed. The humidity levels would get too high and it sucked. Thus, I am passionate about educating people on effectively implementing these schedules. So to sum it up, here are the pros and cons of supplier temperature reset schedules. Pros include a reduction in reheat requirements. It also reduces overcooling the space, which effectively reduces the load back at the chiller. The cons come from when we program in too aggressive of these schedules. They include increased space humidity levels, as we just saw, and a potential for higher fan energy consumption. We do have another reset schedule to discuss today. It is that of the static pressure reset schedule. However, it is probably best to defer that to the last topic of the lesson and first discuss the concept of pressure dependence versus pressure independence and how this applies to our VAV systems.